Here we go.
Hi, I'm U.S. Senator Rob Portman. I really appreciate this opportunity to thank you for your efforts to protect Lake Erie.
A real treasure for Ohio and
the rest of the country. I want to offer a special thanks to Dr. Jeff Reuter and his team at Stone Labs for the work they've done to highlight the continued threat that harmful algal blooms pose to Lake Erie and our freshwater resources. The information that they've provided and will provide today is critical, both to understand the extent of the issue we face and to prepare a comprehensive and effective strategy to combat it.
Last week, following a
fishing trip on Lake Erie with other Ohioans concerned about the lake, I participated in a roundtable discussion with Jeff and others to discuss ways we can work together to protect Lake Erie. I'm encouraged by the fact that folks are working well together. I think we'll be better equipped to address this problem now that legislation I authored with Senator Bill Nelson of Florida has become law. That's the Harmful Algal Blooms and Research and Control Amendment Acts of 2013, just signed into law by the President. For the last decade, this program has served as the federal government's research and response framework for harmful algal blooms. It had not been reauthorized for
in this version, I was able to negotiate a new Great Lakes section for the program.
4 or 5 years. In this version, I was able to negotiate a new Great Lakes section for the program that will, for the first time, ensure that federal agencies prioritize monitoring and mitigation efforts on freshwater bodies, such as Lake Erie. We got a specific reference for the Great Lakes. It's so critical for our tourism and fishing industries, critical for our drinking water, and again, just a treasure for our state. We've got to be sure we're doing everything we possibly can at the federal level to be a good partner. A lot of folks who are with you today were part of helping us be sure that that legislation did address the problems we're experiencing in Ohio. These are good first steps. We know, though, that in the end it's going to take all of us joining together to protect our lakes and rivers from harmful algal blooms. We've got a lot more work to do, but I'm confident, again, that working as a team, that we're ready for the task. So good luck today, and again, Godspeed in your important work. Hope to see you all soon.
Appreciate Senator Portman's work, and obviously it's important to all of us on the Great Lakes. We're now going to transition to Tom Bridgman, probably the second one there, Tom. Oh, okay, there we go. Okay, and Tom's going to tell us about the work that's been going on at the University of Toledo and really about the algae and the nutrients. And I consider the next speakers to really be the meat of this presentation and the important part. And I encourage you, when we get to the discussions and the questions, to look to this group. I consider these people the real experts in this area. We're loading up that presentation.
Do you have any questions for us?
No.
Okay.
No questions at this point. And this is coming up pretty fast. We're hearing from a number of the attendees that my speaker has been too loud. You would really laugh at us if you saw the way we are piecing this together to bring this to you. And again, I apologize. Yeah. There we go. We have a winner. Tom, Dr. Bridgman, at the University of Toledo. I'm going to turn this over to you.
Thank you, Dr. Reuter, and I'll try to hold the microphone really close. If I hold it too low, you probably hear my lunch digesting. So I'm here today to talk about some of the monitoring and tracking of harmful algal blooms that we've been doing in Western Lake Erie since 2002. And that roughly coincides with about the same period that we have satellite data available as well. I want to talk a little bit about the kinds of harmful algae that we have in Western Lake Erie. Most algae are beneficial, diatoms, green algae, and so forth, but certain kinds of algae, or actually they are cyanobacteria, a photosynthetic bacteria that acts like an algae. We have several species in Lake Erie. Anabina, Aphanosomnon, and Microcystis are the most common, and the one that we worry the most about is Microcystis. Those are the ones that we have blooms of that are most obvious, and when you see satellite photos and pictures, it's usually microcystis that you're looking at. And these are of concern because they produce toxins that can be harmful to human health and animal health as well. Let's see. I am advancing. Hang on. Oh, okay, got it. So when we worry about harmful algae and we're concerned with it, we focus on phosphorus. And the reason for focusing on phosphorus is because that is the nutrient or component of fertilizer that is most likely to grow harmful algal blooms. And this figure illustrates that. This is just taken from a standard limnology textbook, and it shows that when you have low phosphorus levels, as on the left side of this figure, you have a diversity of different kinds of algae, diatoms, golden algae, cryptophytes, green algae, and so on. But the higher the concentration of phosphorus in the water, the more the cyanobacteria begin to dominate the assemblage. And by the time you get to about 100 micrograms per liter of total phosphorus, which is about what comes out of the Maumee River, the phytoplankton assemblage becomes almost completely dominated by cyanobacteria. And we knew this back in the 1960s and 70s, and so a lot of remediation efforts were focused on phosphorus. The Great Lakes Water Quality Agreement limited phosphorus, and it had an effect. Through the 1970s and into the 80s and 90s, algal biomass and concentration in Lake Erie decreased significantly. But then in the mid-1990s, things began to go the other way. We saw an upsurge in phosphorus loading from the tributaries, and with that came the return of higher algal biomass, and also a lot of that was cyanobacteria. So we've been tracking blooms now in western Lake Erie for the last 13 years, and I just want to show, let me get back here. This figure's not showing up. There's a figure here showing western Lake Erie. It's just showing our sites, but it's not showing the map. And we sample 6 sites about every 2 weeks throughout the growing season, from about April to October. We use a plankton net, which catches most of the cyanobacteria. We also measure nutrients in the lake as well. Now, these 6 sites are really a snapshot. They're not meant to measure the entire lake, but what they do provide is a good year-to-year comparison. Let's see. Oops, sorry about that. Problems here. Okay. I'm a Mac person. So what we come up with at the end of a year, as we're tracking the blooms, we come up with sort of hump-shaped figures that look like this for each year. Whereas now, right now we're in early July, so we are before the increase. There's really not much harmful algae, cyanobacteria out there right now, but it usually increases in late July, August, maybe peaks in August or September, and then dies off again by early October. And so you get a mound-shaped figure that looks like this. And to compare years, we just look at the area under these curves. So for example, 2002 was a relatively low bloom year. You see a small red area there. And in contrast, 2009 was one of the higher years, and so you see much larger bloom area under there. So that represents the bloom for that year, and then we translate that and we convert that into a bar figure. And so the bar figure is coming up here. Just to give you some context, 2002, the first year that we did our monitoring, was a relatively good year. Western Lake Erie was clear in August, the water was nice and blue, and the bar on the figure is a small bar in 2002, not much microcystis. In contrast, 2003, the next year had a much larger bloom. That was the first large bloom that we have good data for. There had been some other smaller blooms in the late 1990s, but we have good data on 2003 and see how big that bar is and how much of that, how much of the western basin was filled with green algae. So now to show you some of the rest of the data, 2003 was a very large bloom at the time, but now it has been eclipsed in several years since about 2008. And 2003 would now look almost like an average bloom. So what obviously what obviously you can see most prevalently on this figure is the 2011 bloom, which dwarfed all the other blooms. So it's by far the worst bloom we've had so far. 2012, it's a much smaller bloom. It was a much drier year, much less loading from the tributaries. It was a drought year, and so we had a much smaller bloom in 2012. The 2011 bloom was the largest on record, filled the western basin, and spread out into the central basin. And in contrast, comparison, the 2003 bloom looks small now by comparison. So to add in 2013, this is last year's data, 2013 turned out to be the second largest bloom that we've had since 2002. And it was about 2/3 the size of the 2011 bloom. And that's looking at all of our sites. If we look at the nearshore sites, again, the map's not showing up, but I'm just looking at our Maumee Bay nearshore sites now. If we just look at those sites over the years, the nearshore ones, the 2013 bloom was much worse in the nearshore areas than any of the other preceding blooms. And that had a severe effect on especially the water utilities along the southern shoreline. You can see on the satellite photo that winds from the north pushed the bloom along the southern shoreline. It was especially concentrated along the Ohio shoreline of western Lake Erie in 2013. And the consequence of that was that one water utility, Carroll Township, had to take their water offline and issue a do not drink warning. And the city of Toledo, almost lost their water supply, and came very close to reaching levels of toxins that would have caused the city of Toledo and surrounding suburbs to not be able to drink the water. So this was a real problem in 2013. So in some respects, 2013, even though it was a smaller bloom, had more severe effects than the 2011 bloom. All right, I don't know what's on this figure. So a few of the reasons that the 2013 bloom also may have been caused additional problems was because it was a windy year in 2013, and that broke up the surface scum of the cyanobacteria. Usually, as you see on the figure on the right, if it's calm conditions, the microcystis will float on the surface, but if it's windy, the wind will mix it downward. And this was the usual state in September of 2013, and so the microcystis was mixed downward into the water column where it could get sucked into the intakes of the utilities. So that may have been one of the reasons that they had such a high toxin levels in their incoming water. There's been a few recent developments as we look at this, how the relationship of the bloom is to the loading of the tributaries. And one of the things that has come out now is that we think that the lake is now predisposed to having blooms more so than it was, say, 12 or 13 years ago. A given amount of loading now is more likely to produce a larger bloom than that same amount of loading would have caused maybe 12 or 13 years ago. And this is a study coming out of the University of Michigan. And we're still speculating as to why the lake seems to be predisposed to having blooms now. And that could be partially because there's now a large buildup of microcystis seed stock in the sediments now. So there's a lot of overwintering cells that are primed and ready to be reactivated when the weather conditions warm up the following spring. So that could be a condition, a reason. And we also may be seeing some effects of climate change. For example, in 2013, the summer was extended almost into mid-October, and the bloom kept going. And so that may have had an effect. And I don't know if that was just 1 year, but in general, if we tend to have warmer summers, that will extend the growing season for these cyanobacteria. And if we tend to have more intense spring rainfall events, that could drive increased loading of nutrients to the lake. And so in summary, although the annual size of the blooms is somewhat predictable, the effect of the blooms on utilities and beaches and so on is not quite as predictable, because that depends on short-term weather events or vertical mixing patterns. And in summary, Lake Erie may have become more susceptible to harmful algal blooms over the past decade. And so we'd see an immediate beneficial effect of decreased loading as we did in 2012. It still might take several years of low phosphorus loading before Lake Erie heals completely. So with that, I will turn it over to Justin. It's loud.
It's really. Can you hang it over just the front of the thing?
I just set it.
Because they're saying it picks up the background people better than the speaker.
Let's try this.
Yes, it's turning our way.
Here.
This is that little dot out there.
Seems like you're speaking.
I'm trying to get it to hang the right way. Hopefully the black dot facing it. So how about that? If let's stood right there and spoke. Is that better? We just hung the microphone on the monitor. Still loud? With this matter right here, this little plus and minus, I can make it. You tried that already? Okay. Try.
You said, yeah, that's fine.
Okay.
Good.
All right.
Ready to go?
Okay.
Give it back to us. Sorry for the loudness.
Do you want me to just continue on? Or?
Our next speaker is Dr. Justin Chaffin. Justin received his PhD working with Tom Bridgman on this issue, and he's now our research coordinator at Stone Lab, continuing to focus on this issue. So, Justin, it's all yours.
So far today we've been talking a lot about phosphorus, and presenters after me are going to talk a lot about phosphorus. But I'm going to just show a few slides talking about the importance of nitrogen in the cyanobacteria blooms for Lake Erie. So our forecast right now is based on phosphorus, and it works pretty good. When we have high phosphorus loadings during the spring, we're going to have a big bloom. When we have low phosphorus loads, we're going to have a small bloom. But there's more to that story than just phosphorus. And experiments that we've been conducting in Lake Erie, and these experiments been conducting around the world, have we learned that during a cyanobacteria bloom, that nitrogen limits the cyanobacteria abundance. And this is this photograph of a picture that we did in Maumee Bay a couple years ago, where we go out to the lake, collect lake water, bring it back to the laboratory, and we spike it with phosphorus, nitrogen, or phosphorus and nitrogen. And if you look at the picture, you see that adding phosphorus stayed the same, was the same as the control. But you see when you add nitrogen, you get a lot more growth than adding phosphorus. And this happens every year in Lake Erie. We saw this in 2010, which is about a medium-sized bloom. 2011 we saw it, which was that huge bloom. And we saw it in 2012, which was that really small bloom. And this occurs when the ambient nitrate concentration is less than 1 milligram of nitrogen per liter. Uh-oh. Okay, well, I'm missing some graphs that are very similar to what Laura Johnson will show you later today. That if you look at the nitrogen and phosphorus loads to Lake Erie during 2013, apologize the graphs aren't showing up. They showed up earlier. But in 2013, we had a phosphorus load that was just above our long-term average, but the nitrate loading was even higher than the long-term average relative to phosphorus. And you see the text that they decided to put text on this slide. The nitrogen loading was 126% of the long-term average, whereas phosphorus was 111% of the long-term average. And we underpredicted the size of that 2013 bloom based on phosphorus data alone. Wrong way. And nitrogen is also important for the cyanobacteria because they produce toxins. And the toxin that we're most concerned about is microcystin, and this toxin is 14% nitrogen by mass. And you see in the molecule, all those blue circles are highlighting where there's a nitrogen atom. And the main species in Lake Erie, Microcystis, cannot produce microcystin without a nitrogen source. So it needs nitrate, ammonia, or urea, or other forms of organic nitrogen to grow and to produce these toxins. And also when you do those experiments from my first slide, if you spike a bloom with nitrogen, you're going to get more toxins. So just a summary, phosphorus is the most important. We shouldn't lose sight of phosphorus, but nitrogen does play a role, and nitrogen availability will determine the toxicity of a cyanobacteria bloom, and it will also determine the type of cyanobacteria during the bloom. And once you have a bloom, adding extra nitrogen can only exacerbate the problem. So,
very good. Thank you, Justin. We'll make a quick transition to Dr. Laura Johnson from Heidelberg. Dr. Johnson is going to be speaking about the loading of both the discharge and the loading of phosphorus to Lake Erie, and this is really what a lot of the modeling work that we're going to hear from Dr. Stump is based on, and we're extremely fortunate that Heidelberg's been able to gather this data over a period of almost 40 years now. It's a tremendously valuable data set, and there's really no other data set probably like this in the world, and it allows us to make some predictions and do some analyses on Lake Erie that probably couldn't be done anywhere else in the world. And this looks like it's just about up, and Dr. Johnson, and I really encourage people to think of Dr. Johnson as the sort of the go-to person now at Heidelberg for this kind of information, now that Pete Richards has retired. And let's see, this should be up here in just a second.
So maybe I should. Great. I don't know why it's not.
Here we go.
It's just.
Again, I apologize for the delay.
Okay. Maybe I have to fix so far.
It could be the file is just that large.
I didn't think it was particularly like that.
Matt, are there any questions that have come through?
Yeah, I have a few questions.
Here we go. Hold on, Matt. Okay, Dr. Johnson, I'll turn this over to you and let you proceed.
Great. So I've heard that I sound a little bit better if I'm standing to the side. So unless I look over at Jill and she tells me to stop, then I will just stay over here. Okay. Before I get started, I just wanted to mention I am from the National Center for Water Quality Research, and for those of you who are unfamiliar with where Heidelberg is located, I'll put a little star on my figure here, and it's right in the middle of the Sandusky River watershed, which is right next door to the Maumee River. Now, the data I'm going to show you today are collected from the Maumee River as a part of our long-term tributary loading program. Across these 16 different stations that you see in this map here, we've been collecting water quality, some of which since 1975. And you can see we get up into Michigan with the River Raisin. Now, each of these stations is paired with a USGS gauge, so we can use their very highly accurate discharge numbers, put that with the water quality samples that we collect 1 to 3 times a day to get very accurate loads. Oops, I pressed the wrong one. There we go. For the Maumee River, the star just popped up. We began monitoring in 1975, and one of the reasons this is of interest is because it is the largest watershed that feeds into Lake Erie, and also because a lot of the inputs from the Maumee come from agriculture. The watershed is 73% agriculture, land use. So before I get started, I want to first make sure that we're all speaking the same language. I go through a lot of terms, and so I wanted to explain those first. I'm going to be speaking a lot about load, which is basically a mass of the nutrient. In this case, I'll be talking about phosphorus, so the mass of phosphorus over some amount of time. For an annual load, it's usually metric tons of phosphorus per year. We also have, and essentially load is calculated as a product of concentration, which is a mass per unit volume, times discharge, which is how much water is going through the river, which is a volume per unit time. And one way to conceptualize this is by using iced tea. So here's my glass of iced tea. And I'm from Virginia, and down there we like our iced tea rather sweet. So if I put 3 cubes of sugar in this glass of iced tea, that would be pretty sweet sugar. There would be a high concentration of sugar in that volume of tea. But let's say that you don't really like very sweet tea and you want to dilute it a little bit, but you could put the same amount of sugar in a much larger glass of iced tea. It'd be less concentrated. It wouldn't be nearly as sweet. But if either of us drank one of these glasses, we'd get the same load of sugar. We'd still get 3 cubes of sugar. Now, if I was particularly thirsty and I wanted to drink, say, 2 glasses of iced tea in the same amount of time that you drank 1, well, then I would get twice the amount, or twice the load of sugar that you would get. So if you replace sugar cubes with phosphorus and sweetness with concentration of phosphorus, then that's how you can conceptualize the data that I'm going to be speaking about later. So what have we been finding? We've been measuring phosphorus, dissolved phosphorus in the Maumee River for quite some time now. And what I'm showing you here is dissolved phosphorus. I have this picture of an Erlenmeyer showing clear water. So dissolved phosphorus is essentially what's left over after you filter out all the particulates. And if we look at our annual load, so phosphorus exported to the lake over a year, since 1975 we saw the loads decrease until about the mid-90s and have since increased. So I would say this is probably our famous U-shaped curve of dissolved phosphorus from the Maumee. And I want to point out that this is for the water year, so it's October through September rather than our calendar year that we normally think of. But if we look at I did this last time, and this is the text that goes with it. We think this is occurring because of a combination of both increasing concentration of dissolved phosphorus as well as discharge, which both go into calculating load. Now, if we look at the spring load, you can see that, of course, the load's smaller because we're only looking at 4 months of the year, March through June. However, we still see a very highly significant U-shaped curve, as well as I want to point out that the spring loads are on average 45% of the annual loads, meaning that we're getting a disproportionate amount of loading from only 4 months of the year. Now, if I zoom in on the spring loading, we can look more closely at the 2011 and 2012 data. And although the annual loads are pretty similar between these 2 years, if we look at the spring load, you can see that 2011 was the highest spring loading that we've ever measured across our period of record. And 2012 was among the lowest dissolved phosphorus loads that we've measured, not the very lowest. And those were the 2 years that we had the extreme bloom in 2011 and then a very minimal bloom in 2012. So this really points out why we're looking at spring loads when we're doing these types of forecasting. So the big question is, what do we find this year? What do we find this spring from March through June? I've been tracking it every day, it seems like. So this is showing the daily load, the metric tons per day of dissolved phosphorus starting March 1st through June 30th. And basically you can see that early on in the period we had 2 big loading events, mid-March and mid-April. You know, the spring thaw with the rain event on top of it, and then just a lot of rain in April. And if we look at discharge, this is daily discharge in cubic kilometers. You can see that those big loading events are associated with a lot of discharge, which makes sense because load is half discharge, right? But what I want to show you is the cumulative loads, where we actually take each of these days and we sum them together over the period to figure out what that total load for the spring was. And you can see what that looks like for dissolved phosphorus. You can see here now that these first two big loading events really contributed almost all of the spring loading that we found. We had another rain event in mid-May, and then since then we haven't had a whole lot of increase in loading. We can do the same thing for discharge, and it basically looks the same. So how do these compare to our previous years? Now, I'm starting here with discharge, so this is in cubic kilometers over the same time period. What's in gray is the range from 2000 to 2013. The bottom end of that range is basically the very lowest loading you might have cumulatively for that time of the year. The higher end would be the max. And right through the middle here is the mean. And the mean is basically the mean over that same time period, which comes out to be about 2.66 cubic kilometers. Bringing up the top end of the range is 2011, which you know is our big bloom year, and that was at around 5 cubic kilometers. And on the very bottom end is 2011, which is around 1 cubic kilometer of discharge. So in 2013, you can see that we came out, this is in purple, it came out just a little bit above the mean in terms of discharge, and it's at 2.78. For 2014, we're a little bit higher than that yet, and our final number here is going to be 3.32 cubic kilometers for this spring. Let's switch over now to dissolved phosphorus. You can see I've already popped in all of these years. The mean for dissolved phosphorus over this 13-year period is 207 metric tons. In 2011, we were up to 429 metric tons, and in 2012, we're down at 63. So you can see that's a pretty wide range of DRP loads. For 2013, we came up again just above the mean at 240 metric tons. And in 2014, we are a little bit higher than that at 293 metric tons. But I want to point out we're nowhere near as high as it was in 2011. And I guess one thing that I meant to point out earlier this morning, but I didn't, but if you look at that mid-April period, you can see that there was a small period of time in which we were exceeding our range, and you can guess that we were probably getting a bit nervous there, wondering what the rest of the season was going to look like. Luckily, we didn't get many more loading events after that. So if we put these both together, you can see that discharge and spring loading really do mirror each other pretty closely. We did get a little bit more phosphorus earlier in the year relative to the mean and relative to what we saw in spring discharge, but overall we're just a little bit above 2013 for now. If there are any other questions, if you want to see any of the other metrics that we measure, if you want to look at any other stations that we monitor, go to our website. Feel free to email me, or you can contact me through our Facebook page. And with that, I think we can move on.
Very good. Thank you, Dr. Johnson. We're going to make a quick transition now to Dr. Richard Stump from NOAA at Silver Spring, Maryland. And we are going to, based on the way this operated for Dr. Chaffin, we're going to try to switch Rick's presentation from a PowerPoint to a PDF, which we should be able to pull up pretty quickly here. In the meantime, Matt, you indicated that there might be a question or two that was in there.
Yeah, I'm combining some questions. One is, where does the nitrogen in the lake come from?
So the first question is, where does the nitrogen in the lake come from? And that might be a Dr. Johnson question. Where does the nitrogen come from? Do you want to come up, Laura, and address that? Dr. Chaffin, you may want to comment on that also. We probably ought to just stand right up here around it. Tom, when we get to the questioning, you'll have to come up here with us, and I'll just kind of moderate between the five of us.
So I think that the nitrogen loading that Justin showed earlier was data that was collected basically in conjunction with the data I just showed. So we monitor and measure nitrate and ammonium and total Kjeldahl nitrogen the same time that we're measuring dissolved nitrogen concentrations from the Maumee River. Does that answer the question?
And I think you may want to comment also on the way nitrogen might be applied, when it might be applied from a fertilizer situation on farms.
Oh, sure, yes. Yeah, so agricultural nitrogen fertilizer usage, and essentially what happens is farmers tend to apply nitrogen fertilizers right before planting crops as a row starter. That's usually about 30 or 40% of what they apply. The rest of it goes on right beside the corn, right after it's maybe at most a couple feet high, soon after it's been planted. And then there's some that goes on in the fall. So we tend to get big peaks in nitrogen concentrations, particularly nitrate, in June and July, but the loading might not be that big depending on what discharge is.
Right. In that June or July concentration and loading would be coming from the side dressing that farmers might be applying to their corn.
Yes, I believe so. Yep.
All right. And Justin, you want to comment on that also?
The nitrogen can also come from the atmosphere through nitrogen fixation. And also within a lake, well, once nitrogen gets in an algal cell or whatever, it is recycled quite quickly from the sediments or through microbial action. So looking at nitrogen loading is only a small part of understanding nitrogen, because it's coming from atmosphere and from within the lake itself.
Okay, thanks, Justin. We'll take more questions at the end, and now I really want to get to the forecast with Dr. Rick Stump from NOAA. And Rick, I'll turn it over to you.
Thank you, Jeff. Glad to be here. Glad to be back at the lab, and
good to have you.
Thanks for having me. So what we're capturing now is the what we have for forecast for Western Lake Erie for this year. In order to do the forecast, I should note there are several components that we have to get this to happen. A key part, of course, is in order to determine the severity of the bloom. I think you're, and we have been using satellite data for that. And what I show here is we are doing a quantitative method rather than just trying to interpret the true color visible imagery. And so the method here, we come up with a total biomass for the bloom, and we developed that with the MERIS sensor, which had been on the European Space Agency's NVSAT. And we've since transferred, done a similar one to get it to transfer to MODIS. Okay, so we have that component. We also need to understand the data, and we're now in the 6th year of our harmful algal bloom bulletin, which we issue every week, and we pull in field observations that NOAA collects through Great Lakes Lab, and also University of Toledo and Ohio State collect. And that information and that continuous monitoring gives us the understanding and high level confidence in the data we're actually working with, so that we know how it works. And we also have looked closely at 5 years and now coming up in 6 years of data in order to do this. And the last part, next slide, is a key part which you just got from Laura, and that's we need the nutrient load data, because we have the observations on where the bloom is, but in order to do the climatology for a model, you have to have the necessary inputs. So that causative data is critical to that. So we get to where the blooms have been in the last couple of years. 2011 was, as you'd heard before, was the worst, perhaps the worst bloom documented. And 2012, in contrast, had a very calm bloom, and I think you can see in the left image the bright green scum in this October point 2011 and a fairly mild 2012 condition. Next. In 2013, we had also found from our data, which I'll show in the next figure, but not yet, similar to Tom, it was the second most intense bloom. This was very concentrated in the Western Basin. And on the upper section, you can see the true color images, where you can see no bright colors or greenish colors outside the Western Basin. And if you look down at the actual biomass measure, the CI biomass index, you can see how 2011 it spread out well out to the east, in fact, past Cleveland, on the Ohio coast, and even on the Canadian coast. But in 2013, it stayed pretty much in the Western Basin the whole time. That was the result of these, produced other impacts as well. So we have a 12-year time series, and this shows the time series for the different years. You get an idea of years that were very mild and very severe. 2002, I think 2005, 7, and 12 were the mildest years, and you can see the more intense years. And so we use this to come up. We actually accumulate the total biomass in the western Lake Erie related to these blooms in order to come up with an annual metric, and that's the. And then we use that and use the spring discharge in phosphorus to loads to estimate the bloom biomass. We have our paper in PLOS One that we developed in that. There's some other models going on as well. I think University of Michigan has been working one, but similar, using the Heidelberg data in order to do that. So we use March to June loads in order to address this. That's what we determine as the key factor. So if we look through the results in the model and then our forecast for the last 2 years, we have and the black triangles are the measurements we have for each of the years. The red squares are the modeled results, and you can see those closely follow the measured. And then our forecast we made in 2012 and 2013. 2012 we forecast a quite mild bloom, and it was mild, slightly above what we forecast, but pretty close. 2013, while we forecast a significant bloom, we definitely underestimated just how severe the 2013 bloom would be, and a severe underestimate there. What was different in 2013, our model uses the loads from March to June, and 2013 had quite a wet July, and it also had a long calm autumn in September, October. And well, the question might be, if we look at the July discharges for the different years, we see not only 2013 had a high discharge, river discharge from the Maumee, which also equates to high phosphorus loads and so forth, but also 2003 and 2008. And so 2003 wasn't an extreme bloom, nor was 2008 in this scale. So what was different? One thing we found is we looked at temperature data for each of the years, and 2003 and 2008 had quite cold Junes. The average temperature of 64 degrees, about 16 Celsius, and that's at a point where cyanobacteria is not thriving. Whereas in 2013, we're well above, actually above 21 degrees centigrade. And at that point, the microcystis can grow quite well. So our thought is that the growth may not have started at all. So in July of these other years, 2003 and 2008, the cyanobacteria and microcystis wasn't around to take advantage of this sudden influx of nutrients, whereas in 2013 it was. As a result, July was not included in our model previously. So go to the next slide. And this just shows pretty clearly the distinction on these years. 20 degrees is one of the transitions where it really starts growing, and you can see how 2008 and 2003 are well below that. Just as a note, people ask, because this year Lake Erie was frozen over and it was a cool spring, and so the take is, well, what about the rest of spring? Well, if you look at the May temperatures, which are obviously much lower than June, but 2011 was perhaps the coldest May observed, and of course that had the largest bloom. So the spring, which is way too early for cyanobacteria, is not enough to influence it, but we think that June might have led to that. So we go back and look at the other data, and here we're just looking at the dissolved phosphorus in I made a mistake there. That says June dissolved phosphorus. That should be July dissolved phosphorus. Mistake there. So if we have a warm June, then we expect the July load to be a factor in the bloom. In a cold year, we don't expect it. So and if we incorporate that into the model, we can see on the left side the forecast, which is using March to June, the spring model, and then if we add July only during warm years, we can see that they all pretty much fall on the one-to-one line. And 2013 comes in much closer. So our hypothesis is that July matters, provided you have that warm summer condition. So getting to the forecast, you had heard from Laura Johnson, that the the Heidelberg data on the spring loads, and that's the key part of the input. This is a transformation of that data showing the time series for the discharge from the MAMI, the total phosphorus, and the dissolved phosphorus for the spring for all those years. And those are used as inputs into part of the input into our modeling. And so we get from there to forecast. And the forecast we have, we've scaled, we've created a bloom severity index using the data, our data, and University of Toledo's data. And 14 forecast comes out as a significant bloom, and on this you can see that 2011 would be a 10 scale bloom, the worst. 2013, the second worst, is about an A, and we expect this year to be between a 5 and a 6, which is similar to about somewhere between 2009 and 2010. There's the range of variables around the forecast. Those are the maximum minimum of the ensemble of 4 models that we use. So that gives a potential scale range. So we expect a significant bloom of about this category. We're going to start using routinely this index, severity index for it. You can think of it as something analogous to, for example, one of the earthquake indices or the hurricane indices or that sort of thing. So we're looking at a 5 to 6 on that. Now, an important consideration here is that's not a everywhere always. And what I have here are the last 6 years, several of which are significant blooms. And if you look through those, you will see, for example, 2008 in the upper left and 2013, both were very much concentrated in the western basin, pretty much on the Ohio side. In contrast, say 2010, a good section of the western basin close to Port Clinton and the islands in Sandusky Bay had very little bloom. So that there's a lot of variation. That's due to the prevailing wind patterns. If you tend to have northerly winds during the bloom, it'll tend to concentrate on the south coast, the Ohio coast. If you have southerly winds, it'll tend to move up northward and away from the coast. 2009 is rather unusual. It really was dispersed this way, so there were areas with really strong pockets of scum scattered through the area, and then other areas were relatively light, so it was quite variable. So an important consideration is it does change considerably over time. Next slide. And I just show here just the rank, slightly different on the ranking. You can see 2014 kind of puts in the other side. It'll certainly be in the top half of the blooms, again, somewhere around the neighborhood of the 2009-2010 scale blooms. Important thing for understanding the variability distribution, we have the Harmful Algal Bloom Bulletin. Again, this is the 6th year, and weekly we produce the satellite images of where the bloom is, and also quite importantly, we use the circulation models run by our lab in Ann Arbor, the Great Lakes Lab. We use that transport in order to move the bloom in order to predict where it will likely be. Anyone can get that by, if you Google or any other of your favorite search engines, if you search for the NOAA Lake Erie Bloom Bulletin, you will pull it up quickly and you can subscribe to it. So anyone who's interested in getting that information. So you have the ability to know where the blooms are as the summer goes on. And I should emphasize that is not started yet at this point. That's the latest word we have from Tom Bridgman at Toledo. And likely they typically start in early August from the west and gradually expand eastward as we go on. So in sum, we expect to see significant bloom. This should be smaller in 2013 or certainly than 2011. The location extent will be variable depending on the wind, but I should note as a significant bloom there will be areas of scum, there will be areas of green water, unfortunately. The bloom expected to develop from west to east, and the maximum intensity for this sort of blooms, they typically occur not until September. We'll be doing continuous monitoring and updates with help from our colleagues here at Ohio State and also from University of Toledo. That wraps it up.
Very good. Thank you very much, Dr. Stump. And if I could get all of our speakers to come back up again now, and Matt, if you could summarize some of the questions that have come through. We'll take questions for about 10 minutes here, and then end the webinar. And I apologize to the speakers first. You did a wonderful job dealing with an awkward situation, and then to the audience, because you were very patient and a very large number of you came on really 45 minutes late, and we appreciate your patience and involvement. So Matt, what have you got question-wise?
One of the questions is the increase in phosphorus in the 90s, what was the cause of that?
So the increase in phosphorus in the 90s, what was the cause? And do we want to, who do we want to take this? I can address, Laura?
I can go for it. Sure.
Okay.
That's a difficult question to answer, and I'm not really sure that we have a clear-cut answer for anyone on that. There's a lot of things that happened between the mid-90s to today in terms of agricultural practices that have changed. And so to run the gamut of the list of things that we talk about, we have an increase in the size of farms. They've become there's fewer farms and they're larger. So there's heavier equipment on the ground that leads to soil compaction. Because of that, the way phosphorus is applied these days tends to be broadcast, and the timing for that seems to be to apply as much as you can in the fall, sometimes even covering multiple crop years. And I think those are two of the big things that we consider. But the other thing that seems to be coming into play is also an increase in intensity of subsurface tile drainage, which delivers essentially water through these drainage pipes into ditches. And it used to be thought that did not deliver very much phosphorus, but it's been found more and more commonly that there's a lot of phosphorus that comes out of those tile drains. So I think those are the main factors that are causing these increases. Okay.
Let me give a couple more things, and I'd like to ask Tom Bridgman to also comment on what I say now. But essentially, when we look at the loading, we're seeing the vast majority of the loading occurring during severe storm events. And when we look at the 50-year period from 1960 to 2010, we see a very significant increase in severe storm events, particularly on the large storms. The storms that produce about an inch of rain per 24-hour period haven't changed very, very much, but it ratchets up until you get to those storms that are producing over 3 inches of rain in a 24-hour period. And the frequency of those storms for the Midwest, I believe, is up by over 50%. And for Ohio in particular, it's up between 35 and 40%. So you have an increased frequency of the storms, and we know that the loading occurs during the storms. So some of this has clearly been driven by climate change. Now, that's one of the reasons, say, for example, here at Stone Laboratory, that we're trying to do things ourselves. How can we be a good example to address or reduce our carbon footprint, for instance? But the other side of that is that, we can either try to solve this, we can try to immediately reduce or reverse climate change, which I don't think anybody believes is going to happen quickly, or we can reduce phosphorus loading. And those are the two choices, and I think phosphorus loading is a better solution, more immediate solution. Dr. Bridgman, additional comments? Okay. Other questions, Matt?
Yeah. Are the discharges of sediments from Army Corps of Engineers in that same time period, are those correlated with the blue? I guess what we're trying to say.
I'm going to ask Dr. Bridgman to say something about the impact of the blooms, both from a standpoint of the loading of phosphorus and from the work that Dr. Chaffin and Dr. Bridgman have done on the impacts of turbidity.
As far as looking at that pattern of phosphorus loading along with open lake what's the word, not dumping.
Disposal.
Placement. Placement, open lake placement of dredging materials. I don't know that there's anybody who's looked at that time scale of how dredging has changed over that period of time. I believe that dredging has increased as lake levels have dropped because they have to maintain a certain depth in that canal. So I think over the last decade or so, lake levels have dropped, and so dredging would have increased, and so open lake placement would have increased as well. It's still, I think, not completely understood how the open lake placement of dredge materials affects phosphorus levels. Most of that material is sediment from the bottom of the lake, and it contains phosphorus, but the phosphorus usually remains stuck to the particles of sediment even as you move it around. Some may be released, but it's not well understood how much is. There has been a study conducted last year by the Corps of Engineers to study that problem, and that report should be released this month. So I would keep an eye out for the Corps of Engineers report on the effects of sediment placement on phosphorus in western Lake Erie.
Dr. Chaffin, comments about turbidity impact?
Yeah, so algal blooms, the microcystis likes to float up the surface, and when it's at the surface, on a sunny day, it's exposed to really bright sunlight, which in general, algae, cyanobacteria, they don't like high sunlight. But when the water is cloudy due to sediments, it acts kind of like as a sunscreen and helps them thrive better when they're at the surface.
And it would actually probably inhibit the other forms of algae more so than the blue-greens. Okay. Matt, other questions?
Yeah, do you account for contributions of sediment from Ontario in your modeling forecast?
This is Dr. Stump.
Yep, most of the tributaries going directly into Lake Erie on the Ontario side are quite small, so the loads are on the whole quite negligible. Perhaps the one exception is actually rather roundabout. The Thames River, which drains into Lake St. Clair, does maintain an intact plume on the east side of the Detroit River, and we sometimes see small blooms when it comes into Lake Erie, which actually started in Lake St. Clair. On the overall scale, though, these are rather negligible compared to the Maumee. The other thing I should note is Sandusky River, which has about 20% of the flow of the Maumee. It's the second largest tributary. That pretty well concentrates in Sandusky Bay. So Sandusky Bay turns into its own incubator. Occasionally links out, but generally the load is pretty much defined by the Maumee River.
Maybe one or two more questions, Matt?
Are there any variables that negatively affect HABs?
Are there variables that negatively affect HABs?
Drought.
Go ahead, Tom.
Well, obviously the loading of the Maumee River and other tributaries is driven by precipitation. So if there are drought conditions, then whatever fertilizer is put on the land stays on the land. It can't be washed into the tributary. So when we have drought conditions, as we did in 2012, that results in a lower bloom.
Then I'll combine two of these. Are discharges, as the bloom moves further east, are there discharges along the shoreline? Do those make that more severe as it moves eastward? And what is the overall square mileage that you're taking for this year?
Okay, as the bloom moves from west to east, what essentially they're looking for contributions from the other tributaries and other discharge points as you move west to east that would contribute to this. But I'm going to broaden that question a little bit and think about other sources of nutrients as we move west to east. And the other speakers can also comment on this, and I want to let Dr. Stump speak on this also. But when we think of the 2011 bloom as an example, there were some pretty strong indications that that bloom actually grew and expanded as it moved into the central basin. and there are a number of tributaries there, each contributing small concentrations. But we also, when we think of internal loading from the sediment, in the central basin, internal loading plays a much larger role to phosphorus loading than in the western basin. Typically, western basin is very shallow. We're learning more this year about the internal loading through a JLRI grant that Dr. Bridgman, and Dr. Johnson, and Dr. Chaffin are very much involved with. But we know that there's a significant load from the central basin. Dr. Stump, you were going to comment on that also.
When it moves into the central basin, we're typically getting rather late in the season. This happens to be September, October. So we're both in dry periods, so in fact there is very little loading from any tributary, which are already relatively small to begin with. And then we're starting to get to a point where additional growth isn't favored. It's more of tends to be more of a sustaining point of view. So the answer there is we haven't seen any evidence that they drive it, and I think those factors would be so small that we wouldn't be able to address it. The second question was an estimate of the area, and what we've done in the past is we've made an estimate of nominal area. What we found is trying to actually so the nominal area is taking the total intensity, the total biomass, and a relationship we had with that to the square kilometers. Trying to predict the actual area is much harder because, first of all, area of what? What concentration are we working with? And the other part is it's the total biomass is really what we can best estimate. If someone needs that number and needs that estimate from me directly, I don't have that on the top of my head. We're probably, based on the numbers I recall, we're probably looking about a fourth of the estimated area of 2011. So if I was to guess this, and so if you're a reporter, don't quote me, but it's probably between 1,000 and 1,500 square kilometers.
Thank you very much. With that, I'm going to end our webinar for today. I thank the listeners, the attendees for joining us. I really want to thank the speakers. Wonderful job, and I want to thank the staff up here also at the lab for helping us deal with a very unfortunate situation with our WebEx host, and you guys did a wonderful job making this work for us. Thank you very much, and goodbye.